What is getting for the volume in part A? Let's see. So the radius would be 1/4 of this, right? So this will be 1/3 pi times 7.5 over 4 squared times 7.5, right? I like it. So where's the other one? Dupe. Divided by 448 divided by 3. 27.6, what'd you get again? 27.61 roughly. Inches cubed, I like it. And then this guy, just gotta plug an 8 in there, so that's nice. It'll be 1/3 pi times 8 divided by 4, 2 squared times 8. So you get what now? 33.5? 33.51? Something or other? Yeah, 32.51 cubic inches, roughly. Okay. Yes, sir.
Do you want us to keep the pi separate or multiply it in?
Multiply it out, especially in problems like this, because you're walking, you're doing a tour, and you like ask the cave dude, "Hey, how tall is this stalactite?" 7 pi feet or inches. Again, who the shit are you? So when you have physical problems like this, you definitely want to incorporate that in. Do it like we would say. Part C, you just got to plug in there this relationship, right? 1/4 h. So your volume is 1/48 pi h cubed, right? 16 times 3. I think I know. Is that cool? Is that what you guys got?
C.
For part C, right? C is the one where you just gotta write the volume as a function of height only. So then you plug this into R, right?
Oh, I thought we were isolating H, respecting H.
No. Volume as a function of height. So volume is a function of height. Yeah, not height as a function of volume. That could be part of the problem, but not this one. Thank God, because then the derivative gets. I can imagine cube root of bullshit, and you're like, I did it. I'm sorry.
Yeah.
Don't do that. It would still work. It just makes it a lot worse than it needs to be. Now do the derivative of this, and what do you get? dv dt equals 1/16 pi h squared times dh dt, and you should have identified the things that you need to know. It's asking you, the height is increasing at a rate of a 1/2 inch per year, so that's going to go where? dht, so that's 0.5. How quickly is the volume changing? I want to figure out what dv dt is, so I'll know what that is when the height is 7.75 inches.
In part C, in the first one, is that 1/3 times pi times 1/2?
1/4 h, because this is r squared, and what's r? 1/4 h.
Oh,
Yeah. Diameter is half the height, so the radius is 1/4 the height. It's half that. And then plug it in the calculator, what do you get? I can almost hear you. Let's see. 7.75 squared divided by 2. 5.897? Yeah, I think that's what you said, right? What was it? Inches cubed per year? What was it? Yeah, per year. Yes.
I'm still a little confused for D, why it's
Because I thought we had to use the formula we got in C. So that one's
Oh,
1
yeah,
over
we sure did. So
48, that one's
if
1
I
over
do,
16.
so here's D, so if I do dv dt, it would be 1/48 pi 3h squared, right, times dh dt. 3 goes into 48 16, so that's
Oh,
1/16 pi h squared dh dt, yeah.
Oh.
A lot. Yes, sir.
You just subtract the
Yes.
8 from the 7.5.
Yeah, what's the difference between these two?
5.9.
So here's the thing. Hopefully you guys see this. This, do you see how I did 7.75? Right in between 7.5 and 8. So I know the minute I'm not at 7.75, it's going to be at different rates all around. But 7.75 is a good estimate between 7.5 and 8. So it's sort of like wanting the slope at a point here. So you use this point and this point as a secant line. It's going to make a good estimate for that one in the middle, especially the closer they are to it. So if the height has changed about 1/2 inch per year, so this represents a year, doesn't it? This represents a year. Then I would say the volume should change by 5.9 cubic inches if I let a year go past. So this is a year going past, isn't it? Because height is changed by 1/2 inch per year. So this is a year going past. Sure enough, what's the difference in the heights? Like you said, roughly 5. It is 5.9 if you just use these rounded numbers, which is exactly what the estimate was. Do you guys see the point I'm trying to make? So this is a concrete example of what this result means. Or, calcification or whatever the hell you call it. Instead of concrete. Okay, maybe. So that's part E. This difference is the same as that because this is the prediction for letting a year go by. And this is a year going by. And I'm using a point that would give the best slope estimate between these two. Because the idea is this change only works for right at 7.75. The minute I'm at 7.76, would this be the same? Well, no. You can plug in 7.76 and see it's not the same, right? But if I use 7.5 and 8, two values around this, their change should kind of be similar to the change right at 7.75. So it's exactly the same idea as, let me make it a little bit less extreme. I'm interested in the slope, Jeff, here. So I use this and this. Wouldn't that mimic the slope there? 2 points around it. Unless the function is really freaky, it should do a decent job of estimating it. Maybe you guys. That's why it shows the numbers the way that I did, so that it would come out to be a really decent estimate. Okay. Here's the next thing. So I want to take a step away from this. I like doing this kind of thing to people on a test. Hint. Here. So this is more just straight up classic related rates problems. We'll do this thing and then we'll head out.